Okay, good morning. So we have been discussing about interface reconstruction techniques in the previous lecture. Today also we'll continue our discussion on the same. In general, interface reconstruction is actually one step of the volume of fluid method, where depending upon the known value of the volume fraction, we actually try to geometrically reconstruct the interface. And while we are discussing about interface reconstruction, we are using PLIC approach, piecewise linear interpolation calculation based approach for reconstruction of the interface. So in the previous class, I specifically discussed about the Young's finite difference method. Then one brief idea or introduction about centered column difference method also I have given. So typically in centered column difference method, what we do, at the center of each column on a 3 by 3 stencil which placed on the interfacial cell, we actually calculate the height function using this equation. Once we calculated the height function, then slope in x direction I can easily calculate by using y at I plus 1 minus y at I minus 1 divided by 2h. Okay, so this is how I have calculated the slope. So if I know the slope, then I can write that sine of my, because ultimately I need to decide whether I need to draw a line like this or like this. For that, I will be again calculating the my also. To calculate my, the way we have used height function in the first figure, in the similar way we will be using width function in the second figure. Okay, and this is the equation which depicts how we can actually calculate the width function. Okay, and then from the data of height function, mxc can be given as minus 1 by 2h yi plus 1 minus y I minus 1. Okay, and what is the value of yi minus 1? You can substitute using this. Similarly, yi plus 1 also you can substitute using this. So once you substitute the values of yi minus 1 and I plus 1, I will be getting this slope in terms of minus 1 by 2. K varies from minus 1 to 1, and ultimately my final equation is only in the form of volume fraction field. Is this point clear? So how from this step to this step we are replacing yi plus 1 and yi minus 1 using this equation of the height function. Okay, so once we are replacing this using this equation of the height function, ultimately I am getting the value of slope in some algebraic equation, which ultimately is nothing but involving the volume fraction data of different cells which are part of this stencil. Is this point clear? In the similar way, MYC is also calculated, and this xj plus 1 and xj minus 1 is replaced, and ultimately we have obtained data in terms of volume fraction. Okay, so you can see that the fundamental, while we are explaining, then we are using the height function and width function formulation, but ultimately upon further doing some algebraic manipulations, we are able to produce these slopes only in the form of value of color function itself, and color function will be known to me in each and every cell from its advection equation. Is this point clear? Now, depending upon then whatever way we want to represent the line, if we want to represent the line with reference to x bottom, then I will be using this equation. If I want to represent the line with reference to this rightward direction, then of course I will be using this second equation for representing the line. Okay, now I gave you one example, one idea about this method in the previous lecture as well, that the value of yi minus 1 and yi plus 1 will be estimated correctly for the cells which are containing, in which interface is actually cutting the opposite sides of the cell. However, the cell in which the interface is cutting actually two adjacent sides, there the value of height function will not be correct. Okay, so here you can see this is the scenario where in this particular cell, one side, this side is actually intersected by the interface, and here this side is intersected by the interface. And for this cell, using this equation, if you calculate height function, that comes out somewhere over here. So here you can see the value of height function is actually more in comparison to the actual slope of the interface. So when you will be using this data, you will be getting your line something like this. So this will be your line which is approximated using the equation, but in actual line is slightly different. So it means that centered column difference method, even for predicting only the linear slopes, it will not be working very good if, say, even the linear interface is actually crossing the two adjacent sides of the cell. Okay, then this method can be further improved by using certain ways. So basically what we are doing in this method, we are calculating the two slopes. So out of the two, we can choose any one which is more accurate to the interface profile, and based on that actually we can further proceed for the interface reconstruction. Okay, so here you can see this is the first type of interface reconstruction, and in this interface reconstruction, if you see, the angle with respect to x is what? So this is nothing but my mx. Okay, so mod of mx here will be equal to 1 divided by mod of my, because if I have two normal lines, then their multiplication with slope comes out to be -1. So if I am considering their mod, then mod of mx has to be equal to 1 by mod of my. And in this situation, you can see if this is mx, then your my part will be more, and ultimately this 1 by my value will be coming less than 1. Okay, because what is the value of slope? Sorry, what is my? My is nothing but equal to tan theta. With reference to vertical, how much angle is? This angle is greater than 45 degrees. Okay, is this one clear? So with reference to vertical, this angle is greater than 45 degree. If this angle is greater than 45 degree, then my, which is equal to nothing but tan of this particular theta, and tan theta greater than 45 is always what? Greater than 1. So if this value is greater than 1, I will be getting 1 by my as less than 1. Okay. Likewise, this is the second scenario. In this second scenario, if you see, this angle is which angle? Angle with reference to x is actually more in comparison to angle with reference to y. So in this scenario, I can say that my, mod of my will be equal to 1 by mod of mx, and that will be less than 1. Okay. And now comes the third situation. So basically the issue was coming in third situation. These first two, if first one I use this approach, it will be correct. In second one, if I use this width-wise approach, it will be correct. So here one simple thing you can see that out of these two slopes, in first two cases, which one is giving the accurate estimation? In this case, this is larger, the one which is obtained using the height width function. Here this is larger, the one which is obtained using the height function. So I can say that if we reconstruct the line using the largest slope, that will be giving us better outcome. So what I can do in the third situation, I can actually estimate the slopes at multiple locations, and out of all these slopes, which one will be actually larger, we can proceed with that particular slope value. Okay, so typically what is done, because centered column difference method gives issues when I am dealing with the lines which are intersecting the adjacent sides. So what is basically done, slopes are not only calculated at the center, but slopes are also calculated at forward and backward directions. Is this one clear? So slopes are also calculated at forward and backward direction. So what is done basically, one slope you have calculated at this point, one slope you will be calculating at backward face of this cell, one height function you will be calculating at where, forward face of this particular cell. In this way, what you will be getting, when you are using the value of height function at the center points, then whatever you will be getting the slope, that you will be calling as mxc and myc. When you are using the data from the backward points, then you will be getting slope as mxb and myb. Okay, and then you will be applying the same method in the forward direction, and from there whenever you will be getting the data, you will be obtaining mxf and myf. So in total, to reconstruct the interface, how many slopes we are having now? 6. Out of all these 6 slopes, whichever is actually here, in this scenario, what we will be doing, if we are measuring only with reference to one side like mx, my and mc, then we will be considering the maximum. But if we are calculating all the slopes, then we will be choosing the minimum one, and depending upon whether I am taking the x side slope or I am taking the y side slope, accordingly we can choose the appropriate line equation for reconstruction of the interface. Okay, so the issue which was there in terms of reconstructing the interface profile for cells with adjacent crossings, there this method, comparing out of 6 slopes and then using the data depending upon our requirement, actually makes solution more accurate. Okay, so there you will be finding that the interface reconstruction will be actually precise. So this is one just extension of the centered column difference method. In this way you have to decide that with which slope. If you are only considering the centered approach, then among mx and my you have to choose the minimum one, and with that you have to proceed for reconstruction. But if you are also using the forward and backward difference approaches, then out of the 6 slopes you have estimated, you have to use the one with the highest value. Is this one clear? Next comes, the name of the method is ELVIRA method. So ELVIRA is typically called as efficient least squares volume of fluid interface reconstruction algorithm. Okay, so in this ELVIRA method, you can see that advection of reconstructed interface in a given velocity field, it deals with the amount of exchanging reference phase volume across the boundary of the neighboring cell. That already we know. So here you can see this is the extension. What I told you, that I can also calculate the slope using which method? Backward as well as the forward. So what they are doing now, when they are calculating the slope using the backward approach mxb, then how it is calculated? If this is your stencil, one height function you are determining here and one here, and then you are calculating mxc as, this is I minus 1, I and I plus 1. Okay, so for this central difference method, you are using y at I plus 1 minus y at I minus 1 divided by 2h. When you are considering the backward difference approach, one height you will be calculating at ith point, one you will be calculating at I minus 1th point. So if I am calculating slope on I, then I will be taking present value minus value in the previous cell. Okay, so that is my mxb, which is minus 1 by hyi minus yi minus 1. And in terms of color function, I will be getting this k varies from minus 1 to 1, cij plus 1 minus ci minus 1 j plus k. Okay. Similar way, whenever I will be calculating the slope for forward one, then how I will be doing? Please tell me. For forward one, slope will be nothing but I plus 1 minus I. Okay. So yi plus 1 minus yi divided by h. After this, one error function is defined. One error function is defined using the mean square of errors data. Okay. So can you tell me what is the basis of this error function by just looking into this equation? What is CKL? CKL is the actual value of volume fraction. Okay. And what is C tilde KL? C tilde KL will be the value of volume fraction in the same set of cells once this volume fraction is estimated using the slope which is considered for reconstruction of the interface. Is this point clear? So first approach is similar to the Young centered column difference method, where 6 different slopes are calculated and among them the best one is chosen and with the best slope interface is reconstructed. Up to that point it is working in the similar way. After this, what further is done? One error function is defined, which is defined in terms of mean square of errors, and here you can see what does this error function is having. It is having two summation sign. First summation is from k I minus 1 to I plus 1. It means this is the summation along the row. Second is L, which is varying from j minus 1 to j plus 1. So this is the summation along the column. Okay. And then inside I am having CKL. What it means? It means the sum of all volume fractions in this 3 by 3 stencil. All are clear with this point? So this will be becoming, CKL will be basically becoming the volume fraction at location K and L, which is obtained using what? Best slope. Minus what was the CKL which was available with us. Okay. And then their square. What will be this difference? This difference is nothing but error. All of you agree to this point? Okay. In a particular cell, whatever the known value of the volume fraction was there, that was your true value. Then using that value, you have applied some algorithm which has reconstructed the line. And from that line, you have got some new distribution of volume fraction. All are clear with this point? Now, in actual practice, if your actual interface was like this, then if you are having 100% accuracy of the method, then reconstructed interface should also be like this. If both are same, then whatever the distribution of color function is there in the stencil, that should remain same and your error will be 0. But when we have error, then it may happen that this was my true interface and this is my reconstructed interface. In this scenario, in each cell you can see the distribution of the color function has actually changed. If distribution of color function has changed, then whatever is the difference of this in a particular cell, that difference is this error. Is this point clear? Now what I have done, I have taken the square of the error in a particular cell, and this square then I have added for all the cells in my 3 by 3 stencil. All are clear with this point? Now what will be this value? This C tilde KL and CKL, both of these are nothing but the fractional quantities. These will be having value from in between 0 to 1. So these will be fractional quantity. These fractional quantity, when it is multiplied with h square, what is h? H is nothing but the side of the cell, and in both the sides we are taking uniform grid. Okay, for stencil. So it is nothing but coming the overall, it is the mean square of area error in this particular system. Okay, now what I will be doing, If I take this summation, this is interesting to note. If I take this summation, can you tell me what will be the largest magnitude of this error? Which term will be controlling this amount of error? Please tell me. CKL minus CKL will always be a fractional quantity, and the square of the fractional quantity will always be very, very less. Okay. So I can simply say that whatever is the maximum difference between these two quantities, that maximum difference will be controlling the entire error, because whatever remaining other terms will be there in this, these remaining terms, the square of all these terms will be becoming extremely small. Okay, so I can say in this equation, whenever we will be performing the summation, we need not to solve this entire equation. We will be simply first calculating C tilde KL minus CKL, and whatever the maximum value of that C tilde KL minus CKL is coming for this 3 by 3 stencil, that maximum value I will be multiplying with h square. Okay, that is my error function. Now what I need to do with this error function? Please tell me, what should be my objective? My objective should be to minimize this error function. Okay, so then I will be further applying the optimization algorithm to minimize this value of error function below certain threshold limit. Once I have minimized it, of course, for minimizing this, which parameter I can change? I cannot change h square, it's a grid size fixed. I cannot change CKL, because what is CKL? CKL is my, yes, it is the true value of the color function which was originally we were having. Okay, so C tilde KL we can change by just moving with certain steps in backward and forward direction of the line, by changing the slope of that particular line. Okay, and wherever this error is coming below the critical limit, that will be below the threshold limit, that will be my accurate approximation of the interface. Okay, so this way, whatever the interfaces we are reconstructed using the centered column difference method, the accuracy of these interfaces can be improved by minimizing the error. All are clear with this point? In this point, one part is still unanswered, that how to calculate that mathematically, and that part is how to calculate C tilde KL. Okay, so we are doing one approach now that we know CKL, and then we are trying to reconstruct the interface. But for calculating C tilde KL, my problem has become what? Inverse problem? Is it not inverse? Because what I am having now some line based on this slope mn, but I need to know now the values of what? Area of reference phase, so that I can define 1, 1, 0, 0, etc. Is it an inverse problem? So how to calculate all these area of reference phases, that I will explain in the subsequent slides. Is my point clear? Okay, because what is C tilde KL? C tilde KL is the new value of the volume fraction in the stencil. How we are calculating? We are first assuming that we have a line, and then we have to determine C tilde KL. So how to calculate C tilde KL, that I will explain in the subsequent slide. Okay, the next method is least squares fit method. Okay, so again this is a similar method which first employs either Young's finite difference method or centered column difference method for using some preliminary reconstruction. Okay, so over the entire domain, first we will be doing the preliminary reconstruction. After that, the volume value of alpha is also estimated everywhere. What do you mean by value of alpha? Intercept of the line segment. No, it is not volume fraction. Here volume fraction is actually our color function. Okay, so alpha, if you recall, when I have written this equation, this is my alpha. So alpha is where I will be placing the line, what is the intercept of the line. Okay, So in this method what we will be doing, we will be calculating the value of alpha also at each and every point. All are clear with this point? After that, what we will be doing, a few points we will be selecting in each cell. For example, each at endpoints and one at the center. Okay, and so here you can see, if say this is a true curve, for this true curve what you have done, you have selected 3 points in each cell, 2 points at the corner points. So if you have this type of curve, ultimately what will be happening, whenever you will be approximating this using the any of the method, whether Young's finite difference or centered column difference method, you will be getting some line like this. Okay, you will be getting some line like this, and on this line what you have done, so what is this, please understand this very carefully. This is true interface which we need to reconstruct, which we don't know. And when we have applied the either Young's finite difference method or centered column scheme, then this is the reconstructed interface we have obtained. Okay, so this is my preliminary reconstructed interface. On this preliminary reconstructed interface, what I have done, where this preliminary reconstructed interface is crossing the boundaries of the cell, there I defined 2 points. And 1 point I have defined at the center of these 2 boundary points. Is this one clear? This I have shown only for a single cell. Likewise, I need to do this for all the cells which are present in my system. Okay, a simple understanding you can see from here. Say in each cell, these lines nothing but represents the 3 different preliminary reconstructed line interfaces. Is this one clear? If all these are preliminary reconstructed line interface, then you see this interface is crossing at this edge, 1 point, 2nd point, and 3rd point is mean of these 2 points, that is this. Then this is the preliminary interface, 1, 2 and mid of these, 1, 2 and mid of these. So likewise I will be defining all the points in different cells. Now after that I will be defining again one weighted average error function. Okay, so what is this weighted average error function? Please tell me. When I have written the equation, I have written that y equal to minus mx into x plus alpha. This was my equation. What will be residual of this equation? What will be residual of this equation? Residual will be nothing but yi plus mxi plus alpha. Is this part clear? That will be residual. So what I am doing now, I am taking the square of the residual. Okay, all are clear with this point? Square of this residual is having some weight function w I, and this I am performing from I varies I equal to 1 to np. What is the meaning of this? Yes, all the number of points which are there in my stencil. Okay, so for all the number of points I am calculating this value. Whether I use I1 means if line I am considering with reference to x, or I can also use the line with reference to y. So any of the error function I1 or I2 I can use. What will be now my idea? My idea will be to minimize the value of this error function I1 and I2. Okay, so this approach is a very simple approach which we used in our normal regression analysis. Can you tell me what is the approach we used in normal regression analysis? Simple question I am asking you. In Excel, if I plot x and y and say if these are all my data points, if I do linear fit, what I get? How I get this line? How I get this line in the Excel? Can you give me the mathematical basis for estimating this?
डिस्टेंस निकालते हैं हर पॉइंट से और जो मिनिमम होता है वो.
Yes, so first what I will be doing, here you can see, if randomly I have taken some line, okay, so for that particular random line, this is my point number 1, this is point 2, 3, 4, 5 and 6. What I will be doing, this is yp1 predicted value minus actual y1, this is the y1, okay. So it means this is the difference which I have calculated. I will be taking square of this plus this value and this is predicted value, so yp2 minus y2 whole square. Likewise I will be taking for all the points, and then I will try to minimize this error in such a way so that the overall value of the error is actually least. So that is what I am doing in the least squares method. Here you can see what is mxi plus alpha. This is predicted value. And what is yi? This is the, what is yi? Actual value of the point. Okay, for example, here you can see in this case, this is your actual value, okay, and this is your what? Predicted value. So this way you will be actually minimizing this error function, and ultimately you will be when you will be minimizing for this entire stencil where you are having these broken interfaces, instead of the broken interfaces you will be getting some smooth continuous line over the stencil. All are clear with this idea? How we can improve the interface reconstruction if we are actually using the least squares fit method. Okay, so we will be using our initial preliminary method, and after that we will be defining the error function. Ultimately, what is error function? It is nothing but the difference of actual and the reconstructed interface, and ultimately that we are trying to minimize so that we can get good accuracy. Okay. Okay, so this is all about the estimation of slope. Now, after we estimated the slope, what we need to do? Next step is, what happens once we know the slope? Please tell me. Once you know the value of slope, what happens? I know the line, okay, but whether to place this line at this point or this point, how I will be coming to know? For that I need to calculate intercept of the line, which is alpha. How to calculate alpha? That is now our job. Okay, so typically you can consider that if this is my one cell and this was the interface, then this particular cell, when interface will be represented by a polyline using plique based reconstruction, then I will be getting some straight line segment. Okay, this straight line segment will be dividing this cell into a polygon. Is this point clear? I will be getting a polygon out of this. So how many points this polygon are having? A, B, F, G and D. These are the points which are now present in this polygon. Whenever you are dealing with the 2D Cartesian grid, whatever way you draw the line, you will be every time getting nothing but a polygon. Okay, in any configuration of the line, always we will be having nothing but a polygon. Okay, so if we have to calculate if we have to understand that where this line to be placed, we need to minimize this function g of alpha, which is nothing but equal to a of alpha minus delta x delta y into c. What is delta x delta y into c? Delta x delta y are the two sides of the cell, into C is actually your actual area of the reference phase, and A of alpha is the area of the reference phase which we will be getting after placing this line in our two-dimensional cell. Okay, so this error we need to minimize. So ultimately we need to calculate A of alpha. So for calculating A of alpha, there are two methods. This is the first method, which is a deterministic method. So in deterministic method, what is done? If I know all the corner points of the polygon, then how I can calculate area? Please tell me. Half of summation k varies from 1 to n xk into yk plus 1 minus xk plus 1 into yk. Okay, so this is nothing but geometrically, if you see, if you know all the coordinate points of the corners or points of the edges of a polygon, then you will be able to calculate area using this particular method. All are clear with this? So this is approach number 1. So you will be getting some area out of this, then you will be calculating the difference of this area and this, and then whatever this g of alpha is there, we have to minimize this g of alpha. Okay, and how you will be getting this area? This area you will be getting, you already know the value of slope. After knowing the slope, you will be putting this line for any random value of alpha first. Once you have put it for random value of alpha, then based on that you will be getting some area, and then you have to minimize this below some threshold limit to know the actual value of alpha. All are clear to this point? Now the second approach for calculating slope could be based on these triangles which we are having being formed in the adjacent cells because of this interface. So that approach gives area as 1 by 2 mx my alpha square minus function of alpha minus mx delta x minus another function of alpha minus mxy, where f2 of z is nothing but equal to z square for z greater than 0 and it is 0 otherwise. So geometrically, using the data of slopes itself also, we can actually calculate the value of area. Okay, so out of these two methods, can you tell me which one will be more suitable for implementation in numerical solver? So how this derivation is coming for this function, that I am not doing, but of course it can easily, you can obtain this easily, first taking the area of complete triangle and then subtracting this area and this area from the area of this entire triangle, and also you need to take this total area and then you need to subtract. Okay, so if you follow this, then you will be able to obtain this equation geometrically, but I am not going into its derivation. My question is, if say I give you this one as one equation for area calculation and this is a second equation for area calculation, among these two equations, from the perspective of numerical implementation, which one will be easy? First approach or second approach? Please tell me. First one. One important point you need to know that at the moment it may appear to you that it is easy to determine all these coordinate points, but if you are dealing with more number of coordinate points, more is the space in the memory is required, and at the same point of time you also need to maintain more sequence in remembering in what sequence you have the data points. Okay, whereas if you see the second equation, with how many data points you are dealing with? Delta x, delta y, already known parameters based on the cell size. Mx, my, already we are calculating, already we have calculated all the slopes mx and my for each cell. Then, and f is nothing but a simple function which will be equal to square of this quantity if z is greater than 0, like if alpha minus mx into delta x is greater than 0, then it will be square. If it is otherwise, then it will be simply equal to 0. Okay, so only thing here we are dealing with the initial guess of alpha. Okay, so second one is actually more easy to implement in a numerical code. All are clear with this point? Okay, so what is this? This is nothing but three-dimensional extension of this 2D system for interface reconstruction. So can you tell me what the additional things will be coming in 3D? First thing you have to understand, in 2D it was a line, in 3D it will be a two-dimensional surface, and the equation will be equation of a plane, mx into x plus my into y plus mz into z equal to c. Okay, now whenever you will be dealing with three-dimensional interfaces, you have to use one hexahedral system. Okay, so here you will not be having now square or rectangular cell, but you will be having some hexahedral. Inside this, in the neighboring also you will be having one another hexahedral. So this is the representation on a three-dimensional grid. So here this direction shows j minus 1 and j plus 1. This direction shows I plus 1 and I minus 1, and this vertical direction shows k plus 1 and k minus 1. Whenever you will be referring to the centroid of a cell, that will be having now three indices I, J and K. All are clear with this point? Now if you recall, when I explained you the Young's finite difference method, what we used to do in that? We used to calculate the slope at all the corner points, okay, of the cell. So the corner point of the cell is represented with red triangle over here. So all these are nothing but corner points of the cell which is in consideration. So now can you tell me how many corner points we have? 8. So earlier we were doing for 4, now we need to calculate slope for all 8 corner points. And then when we do calculate the slope at the corner points, first we need to calculate the slope at centers of the edges of a 2D grid. Okay. Here instead of center of edges, we have to calculate at the face centers of all the cells. So to represent the face centers, what I am doing, I am using this blue colored cell. So this is representing the neighboring cell centers which are used for estimation of gradients at the face centers. All are clear with this point? And of course, because I have already explained you about the two-dimensional value of estimation of slope. So if you try to extend it, this is how you can extend these formulations for estimation of three-dimensional slopes. Okay, and the way I have given you one equation for area calculation of a 2D grid which can be utilized for estimation of the value of alpha. In the similar way, for this 3D system we will be getting one equation for estimation of the volume. Okay, and the form of the equation is identical to this, but along with this I will be having one mz and more terms involved. And of course in a 2D system I do only have one condition, z greater than 0, but in that scenario I will be having more number of conditions also to approximate this. Okay, is this point clear? So I am not showing that equation, but for the your detailed understanding, if you refer to the book, then in the book you will be finding that particular equation. Okay, so this is the 3D extension of interface reconstruction. Now whenever we reconstructed something, we also need to check that what is the order of error. Okay, so we need to estimate error and we need to also estimate the convergence rate. So for estimating error, we define error function which is equal to 1 by b surface integral of, double integral means I am doing the surface integral. Surface integral of h of xt minus h tilde xt into dx dy. What is h of xt? Actual indicator function. Is this one clear? And what is h tilde xt? Reconstructed indicated function or phase density function, whatever you want to call it. Okay, now the difference of these two will be always error, and I am taking this difference of these two, which will be a fractional value, and then I am integrating over the area. So what will be the unit of this? What is the unit of integral? It will be unit of area. All are clear with this point? It will be unit of area. Now it will depend upon what value of B I consider to determine the overall unit of E. If my coefficient B is equal to 1, then overall unit of this error will be meter square. If I consider B equal to L, where L is my grid size, then what will be the unit of this error? Meter. Okay, so this is a simple thing. For example, in a cell, L is the cell size, this was the actual and this is the reconstructed. Then whatever this area you have got, this area you have converted into a thin strip, and which is, this is distributed over entire L. So the width of this strip is actually represented by the error once you have B equal to L. And if you consider B equal to A, area of the cell, in that case this error function will be becoming dimensionless. Okay, so we will be comparing that what is the value of this error for different methods. And in the similar way, one important term is defined which is called as order of convergence. What do you mean by order of convergence? Log of E of H, like error when grid size was H, divided by error when grid size was H by 2, divided by ln of ratio of grid size to the reduced grid size. This will be coming like this. Okay. So if you see, this table is given for a straight line interface. So if I have to reconstruct a what type of interface? Straight line interface. Then this is done over a 10 by 10 grid, 20 by 20, 40 by 40, because in order to calculate order of convergence, I have to decrease the cell size by 2. So that's why if my initial grid is 10 by 10, to decrease this size by 2, I have to use the grid of 20 by 20. Then further decrease by 2, I have to use grid of 40 by 40. So here you can see one interesting thing. This comparison is between Young's centered and linear fit first method. So if you use Young's approach, magnitude of error in all the columns is in the range of 10 to power minus 4 to 10 to power minus 5. For centered column scheme, it is 10 to power minus 5 to minus 6. And for linear first fit approach, it is from 10 to power minus 6 to minus 8. So it means in terms of accuracy, Young's scheme is having least accuracy, which I have already told you. Okay. And if you see the order of convergence between this to this grid for Young's scheme is almost 1. For this particular scheme, centered scheme, it is starting from somewhere 0.5 and then it is coming close to 1. Whereas for linear first fit, it is almost equal to 1. More will be the value of order of convergence, faster we will be able to reduce the amount of error. Is this point clear? So it means my solution will be converging in less number of iterations. Okay. Then this is the reconstruction for an elliptic interface. So if you have actual interface as ellipse, and this is reconstructed using line segments in different grids. So in first case, this ellipse is in the stencil of 10 by 10 cells. Okay, likewise I have increased the number of cells, and in each line segment this curve will be represented with straight lines. Okay, so here you can see Young's method is giving error in the range of 10 to power minus 3 to 10 to power minus 5. Centered is also giving almost in the similar range. ELVIRA is giving from minus 3 to minus 6, and linear first fit method is giving from minus 3 to minus 6. So error in this method, except for the Young's method, in almost all cases it is of similar magnitude. Okay, but if you see the order of convergence, Young's method is having order of convergence ranging from 2 to 1. Here also order of convergence is ranging from but it is almost staying close to 2. Here it is consistently greater than 2, and here also it is consistently greater than 2. Okay, so this is how you can see the comparison of different methods which are employed for reconstruction of the interfaces. Okay, so once we are having idea about the interface reconstruction methods, our next task will be to study the, what we do once we have reconstructed, what is the next step of finite volume method, of volume of fluid method. Next step is, once we reconstructed interface, then we have to advect that to the what, new time step. Okay, depending upon interface velocity, how it will be advecting with time. So in second step now we need to learn about the interface advection techniques. One example I have shown you while we dealt with the 1D interface advection using different methods like upwind method and the volume of fluid approach in the previous lectures. Okay, so same approach we will now try to see for the two-dimensional interfaces, but that part I will take up in the next class.